What will be tomorrow? Every evening, as we prepare to rest, we ask this question to ourselves. It is perhaps the biggest mystery for all mankind. We can't help but wonder what the future has in store and worry about the uncertainties that may lie ahead. Everyone would like to look a couple of days or years ahead into the future and see what their life will be like. Will I be living the life of my dreams? Or is something really painful waiting to happen? Well, what's the worst that could happen to me? Death. Death shall ultimately claim us all. No one currently in recorded history has cheated death, and no matter how much we try to avoid it or delay it, death will come to us all eventually. Billions of years into the future, when the sun swallows the earth, or whether a cataclysmic event like an asteroid impact occurs, our existence will dissolve into minuscule atoms, scattered throughout the vastness of space, moving haphazardly through the cosmic expanse. We'll return to the very particles that once birthed us. Essentially, we'll once again revert to a state of non-existence. However, the universe will continue its progression. The sun will still rise and set on countless planets. Seasons will change, and the tides will ebb and flow. Stars will be born, and planets will form, sustaining the ever-evolving web of life. The cosmos itself will continue to expand and evolve over time. All events unfold as they have in the past, with the exception that this time, your physical form has transitioned, rendering you unaware of the transformation. Consequently, you may not perceive the alterations transpiring around you. Thus, when you cast your gaze upon the night sky, remember that the stars above may be composed of atoms that were once integral components of a living organism. Space is a realm of possibilities. It is a realm where even the seemingly impossible can be possible. And there are moments when anomalies arise that are hard to explain in a universe governed by fixed mathematical forces. Just look at the night sky above you. Why do the stars, governed by these immutable mathematical forces, scatter themselves in a state of complete anarchy? Why don't stars repeat patterns in the universe? Could this disorderly arrangement be a cosmic message, one that has been overlooked and evaded humanity's attention throughout the ages? A carefully crafted message from an otherworldly intelligence? And what about the countless billions of stars that the infinite universe? How is it possible that we're surrounded by an infinite number of shining stars, and yet the sky remains dark? If the universe is truly eternal and infinite, and the stars are uniformly dispersed throughout the vastness of space, then in any direction we look, we should see a star. The light from these stars, however distant, would eventually reach our planet. Since time immemorial, every human, inquisitive in nature, has thought of these questions at least once. With the advancements and availability of state-of-the-art space tools at our disposal, we find ourselves closer than ever to unlocking the mysteries that have eluded us for ages. It's time to peel back the layers of enigma that obscure our understanding of the cosmos and cast light upon these captivating mysteries of the universe. Take a close look at this picture. This is Eugene Cernan, seen here saluting the flag of the United States, the last person from the Apollo program to set foot on the surface of the moon. However, upon closer examination, you might notice something quite peculiar. There's not a single star to be seen in the background. In fact, every photo taken on the moon during the famous Apollo missions exhibits a sky devoid of stars. Despite the fact that the universe is packed with countless sparkling celestial bodies, even the Apollo astronauts themselves confirmed that they couldn't discern a single star in the lunar sky. This mystery has sparked all sorts of debates and conspiracy theories over the years, with some even using the absence of stars as supposed proof that the moon landing was a hoax. However, the explanation for this mystery delves far deeper than any conspiracy theory. In fact, the resolution to this cosmic puzzle once again leads us to a profound cosmic truth: the Big Bang. Why is space so black? The idea behind this query was first introduced by Johannes Kepler in 1610. our Milky Way galaxy alone contains anywhere from 100 to 400 billion stars, and the observable universe contains roughly 100 to 200 billion galaxies. By this notion, astronomers wondered that since the universe is filled with a seemingly endless number of luminous, light-emitting objects in all directions, logically, every patch of sky you choose to look at should contain thousands, if not hundreds of thousands of stars. This should cause the night sky to be uniformly bright in all directions. Careful analysis suggests that the sky should be as bright as the surface of the sun. This is not the case, however, which puzzled astronomers. It is a paradox that took nearly 300 years to resolve. The paradox had emerged from the steady-state theory, which was the most widely accepted viewpoint on the universe at the time. The steady-state theory said that the universe has been, and always will be, like it is today. Moreover, that the universe was infinite in size, had no beginning, and was uniform in all directions. Initial attempts to resolve this paradox involved speculating that most of the stars were simply too far away to be seen. However, this explanation was quickly dismissed as the steady-state theory itself posited that the universe had existed infinitely long, thus allowing light from even the most distant stars to reach us and contribute to a bright sky. Johannes Kepler came up with a different solution to the paradox by challenging the steady-state theory. Kepler suggested that the stars in the universe extended only to a finite distance, beyond which the viewer encountered only empty space. While this idea seemed plausible, this solution prompted questions. How far away is the boundary, and what lies beyond it? Additionally, the notion of a finite universe posed challenges, such as it would eventually collapse in on itself under the gravitational pull of its stars and planets. This led most astronomers to continue to assume that the universe was infinite, and thus, the paradox and the steady-state theory remained as is, unresolved and forgotten until, after nearly 2 centuries, Heinrich Wilhelm Olbers, a renowned German astronomer, breathed new life into the paradox. Olbers' name has been once again associated with the paradox. Why is the night sky dark? The common belief during his time was that the universe was static, infinitely old, and infinite in size. Olbers had a simple solution. If we assume that the universe is infinite, it is logical to deduce that the opaque bodies in it would also be infinite in number, such as dust and rock, that obstruct the light from distant stars, making them appear fainter. The cosmic dust gradually absorbs and blocks the light of stars as it journeys through space. Even today, most people subscribe to this theory, drawing parallels between it and the way clouds obstruct the sun's light. Cosmic rocks and dust, likewise, could eclipse light from stars. However, Olbers' compelling solution still does not entirely solve the problem, as any rock or dust would eventually heat up and radiate the absorbed energy. The universe would still contain the same amount of radiation. The dust merely acts as a mediator, so to speak, between the stars and the observer. Ultimately, the energy we detect on Earth would be the same. So what's the solution to the paradox? The solution to the paradox would be revealed after a wait of another 100 years. In 1929, when Edwin Hubble peered through his powerful telescope, he hoped for a universe that would be collapsing, as that would prove a finite universe, just like Kepler said. But to his shock, he discovered that the universe was not collapsing in on itself, but rather, the galaxies were moving away from us, as if the space between was expanding. In fact, the further away the galaxy, the faster it was moving away. The universe appears to not be falling in on itself, not remaining static, but expanding. This raised a new question. If the universe is expanding, then what does that mean for the early universe? Cosmologists now believe that the universe was once incredibly small and dense, and that it expanded rapidly in a phenomenon known as cosmic inflation. As the universe expanded, it cooled down and eventually stars and galaxies formed. This discovery ultimately led to the development of the Big Bang Theory, as we know it today. Scientists today think this happened about 13.8 billion years ago. It is the most accurate model of the birth of our universe. Most scientists Think the universe has a finite age and that it started 13.8 billion years ago. When we look at 13.8 billion-year-old light, it's not that we don't see stars just because the light from them hasn't gotten to us yet. We don't see any stars because we're getting a glimpse at the universe before any stars had formed. A starless universe. The farther we look, the farther back in time we observe, until we reach the edge of the universe. This is not a physical edge, but instead the afterglow of the Big Bang, known as the cosmic microwave background, the farthest point in the universe that we can observe from Earth. When we point our telescopes past the earliest stars, we see this light. This is not starlight, but the light left over from the Big Bang, forming a background beyond the stars. But wait, the Big Bang theory seems to introduce a new problem. It states that the universe was much brighter in the past, especially at the end of the recombination era. All points of the local sky at that era were comparable in brightness to the surface of the sun, due to the high temperature of the universe in that era. So, the cosmic microwave background should actually be dominating our night skies back on Earth, resulting in a constant need to wear sunglasses all the time, to avoid being blinded by the intense brightness of the universe. Thankfully, this is again offset by the fact that the universe is expanding. The expansion hasn't stopped after the Big Bang. Instead, it has only gotten faster, meaning new space is constantly being created, even faster than the speed of light itself. At first sight, this may seem like a violation of the principle of special relativity, which states that nothing can move through space faster than the speed of light. But in fact, it's not. The expansion of space is not caused by objects moving through space, but rather by the stretching of space itself. This stretching is due to the effects of dark energy, a mysterious force that is causing the expansion of the universe to accelerate. The expansion of space is measured by a quantity known as the Hubble constant, which expresses the rate at which the universe is expanding. Currently, the best estimates of the Hubble constant suggest that space is expanding at a rate of about 73.3 kilometers per second per megaparsec. This means that the distance between 2 points in space will double in size in about 9.8 billion years. Now, as you may know, light is a wave, and as stars move away from us, their light waves get stretched out. The human eye can only see certain wavelengths of light, and when the wavelengths get too long, we can no longer see them. This is called redshift, as red has the longest wavelength of all the visible colors. For very distant objects, the light waves get stretched so much that they become infrared, and we can no longer see them. So, in a sense, the night sky is lit up. We just can't see it because of our limited human eyeballs. But telescopes can, and that is why we get to see such images. So, finally, this is how the solution to the paradox plays out. Because of the finite speed of light and the fact that the universe has a finite age of about 13.8 billion years, this finite age means we can only see stars and galaxies whose light has had enough time to travel to us. The expansion of space-time complicates things even more. In the far-out regions of space, where space is expanding faster than the speed of light, the light from those galaxies will never outrun the expansion. No matter what we do or how long we wait, we'll never be able to see light from those galaxies. It will never light up our skies. What we see in the night sky is just a tiny fraction of the whole cosmos. We call this the visible universe, and we cannot, even with the most powerful telescopes, see beyond this horizon. It isn't just a horizon in space, it's a horizon in time. Beyond the edge of our visible universe, the light will never outrun the expansion. Due to this expansion, much further into the future, about 100 billion years from now, imagine we invent a powerful new telescope, which will allow us to explore space beyond the galaxy. But as we peek through the telescope, we find nothing but darkness and empty space. The generation of people have come to understand that they exist within a seemingly endless and almost informationless void. As the age of the cosmos approaches 100 billion years, the expansion of the universe will cause all other galaxies to vanish beyond the cosmic light horizon. This means that light from other galaxies will no longer be able to reach us. Put another way, galaxies will be pushed aside out of the observable universe and can thus no longer be observed. Today, we lose about 20,000 stars a second. And if you think about it, we are rather fortunate to exist at a point in time when we have access to such an abundance of information. Sure, there are a lot of things about the universe that we do not understand, but at least there's hope that one day we will. The distant future of a 100 billion CE, however, would be so information deprived that when they aim their equivalent of the Hubble telescope towards a seemingly empty region of space, the returned image would also be empty. Of course, the same is true today. We have no way of knowing what lies beyond the observable universe. But one final question remains. Why are these moon pictures devoid of stars? Surely, with nothing in the way, like an atmosphere, we should be able to see some stars in the background. For this, we must learn how color is actually formed. Color is a complex interplay between light and matter. Light is composed of electromagnetic waves of different wavelengths, and when it interacts with an object, some wavelengths are absorbed by the object, and others are reflected or transmitted. The colors that we see are a result of the wavelengths of light that are reflected back to our eyes. For example, if an object appears red, it is because the object has absorbed all the other colors of the visible spectrum, such as blue and green, and reflects only red light back to our eyes. Similarly, if an object appears white, it is because it reflects all the colors of the visible spectrum, while an object that appears black absorbs all the colors and reflects none back to our eyes. We are able to see the blue sky on Earth because particles in the atmosphere act as mirrors. The word literally means atmos, meaning vapor or atoms, and sphere, meaning globe. During the night, the sun sets, and there is no sky to obscure our view of the stars. On the moon, however, there is no atmosphere to scatter light, but still we don't see stars. This is because the light from the sun travels in a straight line without scattering, and all the colors stay together. Looking toward the sun, we thus see a brilliant white light. This is what happened with the Apollo astronauts. Every lunar landing took place on the day side of the moon, even though there was no atmosphere above them. The reflection of the sun's light from the moon's surface made their eyes temporarily blind. The high brightness intensity glare from the sun blinded them and their camera's sight of the stars. Though one astronaut reported being able to see some of the brightest stars when he was in the shadow of the lunar module, looking directly up with his protective visor raised. Imagine, though, if astronauts ever landed on the night side of the moon and had their eyes adjusted to near pitch-black conditions, they would get a stunning view of the stars. If the Earth had no atmosphere, then even Earth's sky would look like the moon's. Currently, taking into account light pollution and the limitations of the human eye, we can see roughly 3,000 stars during the night sky and only about 300 stars on a full moon night. This is why some scientists believe it would be a great idea to spend money and time building a large telescope on the night side of the moon. The enigma of Olber's paradox remains one of the most intriguing mysteries in cosmology, and its solution has provided a deeper understanding of the nature and structure of our universe. Given the millions of billions of Earth-like planets, life elsewhere in the universe, without a doubt, does exist. In the vastness of the universe, we are not alone. Albert Einstein. According to a recent comprehensive survey by Pew Research Center, 2/3 of all Americans now firmly believe that alien life does indeed exist, and at least 51% have full confidence that UFOs reported by people in the military are likely evidence of intelligent life outside Earth. And considering the significant and groundbreaking advances in astrophysics, scientists today firmly believe that there is a compellingly high probability of discovering extraterrestrial intelligence within the next few decades. Seth Shostak, a distinguished astronomer at SETI, Search for Extraterrestrial Intelligence, has boldly proclaimed that, in a mere couple of decades, we will unequivocally uncover tangible evidence confirming the existence of intelligent life beyond our planet. as humanity casts its ever-expanding net across the vastness of the cosmos, capturing evidence of thousands of worlds. One ancient question haunts us. Is anybody out there? The vast expanse of the cosmos, with its many galaxies, stars, and planets, makes it very obvious that there is a possibility for life to exist elsewhere. Even if we accept that the origin of life on Earth was a rare occurrence, the immense size of the universe serves as a large blank canvas for the diversity of life to emerge. It is a landscape that might include intelligent beings at all levels of development, ranging from the least advanced to the most evolved. Just imagine yourself alone, weightlessly floating in the vast expanse of space. The silence can be deafening, and the emptiness overwhelming. At first glance, you may believe you are truly isolated, devoid of companionship. However, contemplate the intricate ecosystems thriving inside our bodies, often taken for granted and ignored. Many microbes and tiny organisms may be living on your skin or within your digestive tract, their existence unbeknownst to you. While these organisms may not possess our level of intelligence, their presence serves as a poignant reminder that solitude can often be an illusion. Similarly, the idea that we are alone in the universe may also be a delusion, unknown to us. Life throughout the universe could demonstrate a vast range of intellect that we unconsciously overlook. Intelligence is an extraordinary feature that has profoundly shaped our own existence, and its manifestation can take diverse and fascinating forms throughout the vast expanses of the universe. On Earth alone, intelligence manifests in many intricate ways, like the social structures of ants and bees, the empathy of dolphins and elephants, and the technological advancements of humans. As we embark on our search for life beyond Earth, we must broaden our understanding of intelligence and life itself. You can only see things that are within the range of your light. Similarly, the observable universe is like our cosmic flashlight's range. Anything beyond this range is invisible to us, not because it doesn't exist, but because its light hasn't reached us yet. The size of the observable universe is enormous. It's estimated to be about 93 billion light-years in diameter. This means that the farthest objects we can see are 46.5 billion light-years away from us in every direction. The reason this number is bigger than the universe's age in light-years is because the universe has been expanding since the Big Bang, stretching the distances. The boundary of our observable universe is known as the cosmic horizon. This is the edge beyond which we cannot see, no matter how powerful our telescopes become. This horizon is set by the speed of light and the age of the universe. Light travels at a speed of about 300,000 kilometers per second, or 186,000 miles per second. Since the universe is 13.8 billion years old, the farthest light we can see has been traveling for that long. However, because the universe is expanding, the objects that emitted this light are now much farther away than 13.8 billion light-years. Our understanding of space has come a long way over time. Ancient civilizations looked up at the sky and saw stars and planets, but they had no idea how far away these objects were. They often believed the stars were fixed points on a celestial sphere surrounding the Earth. Ancient civilizations all over the world developed their own ideas about the universe. These early models, called cosmologies, reflected the knowledge and beliefs of their times. For example, the ancient Egyptians saw the sky as a goddess named Nut arching over the earth, which was her husband Geb. The stars were thought to be jewels on Nut's body. The Egyptians believed that the sun god Ra sailed across the sky during the day and journeyed through the underworld at night, bringing light and life to the world. In Mesopotamia, the Sumerians and Babylonians envisioned the universe as a flat disk floating in water. They believed the sky was a dome with stars embedded in it and that it separated the heavens from the earth. The Babylonians were skilled astronomers and made detailed observations of the movements of stars and planets, using this knowledge for practical purposes, such as creating calendars and predicting eclipses. The ancient Greeks developed more complex models of the universe. One of the earliest Greek philosophers, Anaximander, proposed that the Earth was a cylinder floating in space. Later, Pythagoras and his followers suggested that the Earth was a sphere. This idea was supported by observations, such as the shape of the Earth's shadow on the moon during a lunar eclipse. Plato, another Greek philosopher, believed that the heavens were perfect and unchanging, and that celestial bodies moved in perfect circles. His student Aristotle further developed these ideas, proposing a geocentric model of the universe. In Aristotle's model, the Earth was at the center, and the sun, moon, planets, and stars all moved in circular orbits around it. This geocentric view was widely accepted for many centuries. In ancient China, cosmology was also an important part of understanding the universe. The Chinese believed in a flat Earth covered by a hemispherical sky. They saw the universe as a series of concentric circles, with the Earth at the center. Chinese astronomers made careful observations of celestial events, developed a lunar calendar, and created star maps, cataloging the stars and constellations. During the Middle Ages, the geocentric model of the universe remained dominant in Europe, largely due to the influence of the Catholic Church. However, in the Islamic world, scholars made significant advances in astronomy. Persian astronomer Al-Tusi developed a model that improved upon the Ptolemaic system, which was a refined version of Aristotle's geocentric model. Al-Tusi's work laid the groundwork for future astronomical discoveries. The Copernican revolution marked a major shift in our understanding of the universe. In the early 16th century, Polish astronomer Nicholas Copernicus proposed a heliocentric model, in which the sun was at the center of the universe and the Earth, along with other planets, orbited around it. This idea was revolutionary because it challenged the long-held geocentric view. Copernicus's model provided a simpler explanation for the observed motions of planets, which seemed to move in complex paths when viewed from a geocentric perspective. Despite its advantages, the Copernican model was not immediately accepted. Many people were reluctant to abandon the geocentric model, which was deeply ingrained in their worldview. However, over time, more evidence supported the heliocentric model. In the early 17th century, Johannes Kepler used precise observations to develop his laws of planetary motion, which described the orbits of planets as ellipses rather than perfect circles. Kepler's work provided strong support for the Copernican model. Italian astronomer Galileo Galilei also played a crucial role in advancing the heliocentric model. Using a telescope, he made several groundbreaking observations, such as the moons of Jupiter and the phases of Venus, which were consistent with the Copernican system. Galileo's findings challenged the traditional geocentric view and faced opposition from the Catholic Church. Despite this, his work laid the foundation for modern astronomy. The next major transformation in our understanding of the universe came with Albert Einstein's theories of relativity in the early 20th century. Einstein's special relativity, introduced in 1905, fundamentally changed our concepts of space and time. According to special relativity, the laws of physics are the same for all observers, regardless of their relative motion. This theory also introduced the idea that the speed of light is constant and cannot be exceeded. Special relativity led to the famous equation E equals mc squared, which shows that mass and energy are interchangeable. This had profound implications for our understanding of the universe, showing that energy could be converted into matter and vice versa. It also explained the behavior of objects moving at high speeds, close to the speed of light. In 1915, Einstein published his general theory of relativity, which further revolutionized our understanding of gravity. Instead of viewing gravity as a force between masses, general relativity described it as the curvature of space-time caused by the presence of mass and energy. Massive objects like the sun bend the fabric of space-time, and this curvature affects the motion of other objects, like planets. General relativity provided new insights into the nature of the universe. It predicted phenomena such as the bending of light by gravity, known as gravitational lensing, and the existence of black holes, regions of space where gravity is so strong that not even light can escape. These predictions have been confirmed by observations, demonstrating the accuracy and power of Einstein's theory. Einstein's work also laid the groundwork for modern cosmology. It led to the understanding that the universe is dynamic and can expand or contract. In the 1920s, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, indicating that the universe is expanding. This finding supported the Big Bang theory, which proposes that the universe began as a hot, dense point and has been expanding ever since. In the 1920s, Edwin Hubble made a groundbreaking discovery that changed our understanding of the universe forever. Using powerful telescopes, he observed that distant galaxies were moving away from us. By measuring the light from these galaxies, Hubble found that the light was redshifted, meaning it shifted towards the red end of the spectrum. This red shift indicated that the galaxies were receding from us, much like the sound of a siren lowering in pitch as it moves away. Hubble's observations led to the realization that the universe is expanding. This was a radical idea at the time, challenging the notion that the universe was static and unchanging. The discovery that galaxies are moving away from each other suggested that the universe had a beginning, from which it has been expanding ever since. The expanding universe and the theory of inflation have profound implications for our understanding of the cosmos. They suggest that the universe we see today, with its vast array of galaxies and complex structures, evolved from a simple, uniform state through processes driven by the laws of physics. These discoveries also raise intriguing questions about the ultimate fate of the universe. If the expansion continues, will it go on forever, or will it eventually slow down and reverse, leading to a collapse? Modern observations indicate that the expansion of the universe is not slowing down but accelerating. This acceleration is thought to be driven by a mysterious force called dark energy, which makes up about 70% of the universe's total energy. The nature of dark energy remains one of the greatest mysteries in cosmology, leaving us with questions that push the boundaries of science and inspire our endless fascination with the cosmos. One of the biggest mysteries in cosmology, and understanding it could provide crucial insights into the fate of the universe. The journey from Hubble's discovery of the expanding universe to the development of inflation theory and the study of dark energy highlights the incredible progress in our understanding of the cosmos. The cosmic horizon, the edge of the observable universe, is defined by what we call the cosmic horizon. This horizon represents the furthest distance from which light has had time to reach us since the beginning of the universe. Because the universe is about 13.8 billion years old, the light from the most distant objects we can see has been traveling for 13.8 billion years. However, due to the expansion of the universe, these objects are now much farther away than 13.8 billion light years. The cosmic horizon is like a giant bubble around us, with a radius of about 46.5 billion light years. Anything beyond this bubble is currently unobservable because its light hasn't had enough time to reach us. This doesn't mean that nothing exists beyond the horizon. It just means we can't see it yet. The concept of redshift is essential in understanding the cosmic horizon. When we look at distant galaxies, we see that their light is redshifted. This means the light waves have been stretched to longer wavelengths, or towards the red end of the spectrum, as the galaxies move away from us. The greater the redshift, the farther away the galaxy is and the faster it is receding. By measuring the redshift of galaxies, we can determine their distances and how fast they are moving away, giving us a glimpse into the universe's expansion history. When we observe light from distant galaxies, we are actually looking back in time, because light takes time to travel across space. We see distant objects as they were when the light left them, not as they are now. For example, when we observe a galaxy 10 billion light years away, we see it as it was 10 billion years ago. This light travel time allows us to study the universe's past and understand its evolution over billions of years. The observable universe is only a portion of the entire universe. Beyond the cosmic horizon lies the unobservable universe, regions we can't see because their light hasn't reached us yet. The distinction between the observable and unobservable universe is crucial for several reasons. Firstly, it affects our understanding of the universe's size and structure. The observable universe is vast, but it's only a tiny fraction of the whole universe, which might be infinite. This means there could be countless galaxies, stars, and planets beyond what we can see, possibly even regions with different physical laws or properties. Secondly, the unobservable universe holds clues to the universe's overall shape and topology. Scientists use models and observations from the observable universe to infer what might lie beyond the horizon. These models help us understand whether the universe is flat, open, or closed, and how it might evolve in the future. Lastly, the distinction between the observable and unobservable universe has philosophical implications. It challenges our perception of reality and our place in the cosmos. Knowing that there are regions of the universe we will never see, no matter how advanced our technology becomes, reminds us of the limits of human knowledge and the vastness of the cosmos. Studying the edge of the observable universe also helps us understand the early stages of the universe. The light from the most distant galaxies comes from a time when the universe was very young. By analyzing this light, scientists can learn about the conditions and processes that occurred shortly after the Big Bang. This information helps refine our models of cosmic evolution and the formation of galaxies and large-scale structures. The study of the cosmic horizon and the observable universe connects to many other areas of cosmology and astrophysics. For example, it ties into the study of dark matter and dark energy, which make up most of the universe's mass and energy, but remain largely mysterious. Understanding how these components influence the universe's expansion and structure helps us build a more complete picture of the cosmos. Philosophical implications of an infinite universe. The concept of infinity has fascinated humanity for centuries, extending its roots deep into the realms of both cosmology and mathematics. In cosmology, infinity often refers to the boundless nature of the universe. When we talk about the universe being infinite, we mean that it has no end, stretching out endlessly in all directions. This idea challenges our understanding, as our daily experiences are limited to finite spaces and objects. In mathematics, infinity is more than just a theoretical concept. It is a well-defined idea with practical applications. Mathematicians use the symbol infinity to represent infinity and have developed a rigorous framework for working with infinite quantities. Calculus, for instance, deals extensively with infinite series and limits, allowing us to approach the infinitely small and the infinitely large in a structured manner. Infinity in mathematics helps us grasp the ungraspable, providing tools to analyze and describe phenomena that seem beyond our finite comprehension. When we think about an infinite universe, it poses profound existential questions about humanity's place within it. In an infinite universe, the idea of a central or special location becomes meaningless. If space extends forever, then no point can be considered the center. This shifts our perspective from seeing Earth, and by extension ourselves, as the focal point of existence to being just a tiny part of an immense, perhaps incomprehensible, expanse. This can be both humbling and disconcerting. The notion that we are not unique, but rather a small part of an infinite tapestry challenges our sense of importance and significance in the cosmos. Moreover, the concept of an infinite universe brings into question the nature of existence itself. If the universe is infinite, then it may contain infinite versions of ourselves and our lives, slightly altered in myriad ways. This idea, often explored in science fiction, suggests a multiverse where every possible outcome exists somewhere. While this is speculative, It invites us to ponder the limits of reality and our perception of it. Could there be countless versions of our world, each slightly different from the one we know? If so, what does that mean for our understanding of identity and individuality? These considerations lead us to the anthropic principle, a philosophical idea that asserts that observations of the universe must be compatible with the conscious life that observes it. There are two main interpretations of the anthropic principle: the weak and the strong anthropic principles. The weak anthropic principle suggests that the universe's observed values of physical constants are not random. Rather, they fall within the narrow range that allows for the existence of life. If these constants were even slightly different, life as we know it could not exist, and therefore we would not be here to observe them. The strong anthropic principle goes a step further, proposing that the universe must have properties that inevitably lead to the development of conscious life. This implies a universe somehow designed with the emergence of observers in mind. This interpretation raises profound questions about the nature of reality and the possibility of a purposeful design behind the cosmos. The anthropic principle provides a framework for understanding why the universe is the way it is, despite its apparent fine-tuning. In an infinite universe, the anthropic principle can help explain why we find ourselves in a region where conditions are just right for life. If there are infinite regions with varying conditions, then it is inevitable that some regions will have the right conditions for life to emerge. We happen to be in one of those regions, not because it is special or unique, but because it is one of the few where observers like us could exist. However, the anthropic principle is not without its critics. Some argue that it is a tautology, a statement that is true by necessity but provides no explanatory power. Others contend that it borders on teleological explanations, implying purpose or design in the universe's structure. Despite these criticisms, the anthropic principle remains a valuable tool for exploring the philosophical implications of our existence in an infinite cosmos. Other universes, each with its own unique characteristics. Some of these universes might be similar to ours, while others could be drastically different, with entirely different forms of matter and energy. The concept of bubble universes helps us to understand how the multiverse might be structured. It suggests that our universe is just one bubble in a vast cosmic foam, with other bubbles constantly forming and evolving. This idea expands our understanding of the cosmos and challenges us to think beyond the confines of our observable universe. The many worlds interpretation of quantum mechanics is another compelling multiverse theory. Quantum mechanics is the branch of physics that deals with the behavior of particles on the smallest scales. It is known for its counterintuitive and often bizarre predictions. One of the fundamental principles of quantum mechanics is that particles can exist in multiple states simultaneously, a phenomenon known as superposition. According to the many worlds interpretation, every time a quantum event occurs, the universe splits into multiple parallel worlds. Each of these worlds represents a different outcome of the quantum event. For example, if a particle can be in two places at once, the universe splits into two parallel worlds, one where the particle is in one place, and another where it is in the other place. This process of splitting happens constantly, creating a vast number of parallel worlds. In the many worlds interpretation, every possible outcome of every event exists in its own parallel world. This means that there are countless versions of reality, each slightly different from the others. Some of these parallel worlds might be very similar to our own, while others could be radically different. The many worlds interpretation challenges our understanding of reality and raises profound questions about the nature of existence. The idea of parallel worlds in quantum mechanics is both fascinating and perplexing. It suggests that the universe is constantly branching into multiple parallel realities, each with its own version of events. This concept challenges our perception of time and causality, as it implies that every possible future exists simultaneously in different parallel worlds. These multiverse theories, string theories, parallel universes, the bubble universes from cosmic inflation, and the many worlds interpretation of quantum mechanics all suggest that our universe might be just one of many. They expand our understanding of the cosmos and challenge us to think beyond the limits of our observable universe. The idea of a multiverse raises profound philosophical questions about the nature of reality, our place in the cosmos, and the fundamental laws that govern existence. These theories not only expand our understanding of the cosmos, but also invite us to consider the profound implications of a multiverse. If multiple universes exist, each with its own unique properties, what does this mean for our understanding of reality? How do we reconcile the existence of parallel worlds with our everyday experiences? These questions challenge us to think deeply about the nature of existence and the limits of human knowledge. The exploration of multiverse theories is a testament to the power of human curiosity and imagination. It demonstrates our willingness to question the boundaries of our understanding and to seek answers to some of the most profound questions about the universe. String theory has emerged as a promising candidate for a unified theory, proposing that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. These strings can vibrate at different frequencies, with each frequency corresponding to a different particle. String theory naturally includes gravity and can potentially reconcile it with quantum mechanics by treating particles as one-dimensional objects rather than zero-dimensional points. It smooths out many of the infinities and inconsistencies that arise when trying to merge the two frameworks. Additionally, string theory introduces extra dimensions beyond the familiar three dimensions of space and one of time. These extra dimensions are compactified, meaning they are curled up so tightly that they are not observable at everyday scales. The mathematics of string theory suggests that there could be as many as 10 or 11 dimensions, and these hidden dimensions provide the necessary framework for unifying all fundamental forces, including gravity, electromagnetism, and the strong and weak nuclear forces. M-theory is an extension of string theory that unifies the 5 different versions of string theory into a single framework. It suggests that the fundamental objects in the universe are not just strings, but also higher dimensional membranes or branes. These branes can have various dimensions, and our universe could be one such three-dimensional brane floating in a higher dimensional space. M-theory provides a more comprehensive picture and is considered a leading candidate for a theory of everything. Despite its elegance and potential, string theory and M-theory face significant challenges. One main issue is that they are difficult to test experimentally. The scales at which string effects become significant are so small, and the energies required to probe them are so high that they are beyond the reach of current technology. Additionally, string theory predicts a vast landscape of possible solutions corresponding to different possible universes with varying physical properties, making it challenging to identify which, if any, of these solutions corresponds to our universe. An alternative approach to unifying quantum mechanics and general relativity is loop quantum gravity. This theory takes a different path by attempting to quantize space-time itself instead of treating gravity as a force within a fixed space-time background. Loop quantum gravity suggests that space-time is made up of discrete quantized loops, which are incredibly small, on the order of the Planck length about 1, 0, minus 35, 10, minus 35 m. At this scale, the smooth fabric of space-time breaks down into a network of finite loops. Loop quantum gravity aims to preserve the principles of general relativity while incorporating the quantization methods of quantum mechanics. One key achievement of this theory is the derivation of a discrete structure of space, where space itself is composed of finite loops or quanta of space. This discrete nature could help resolve the infinities that plague quantum gravity calculations. Loop quantum gravity also provides insights into the nature of black holes, suggesting that the singularities predicted by general relativity are replaced by finite quantized structures. Another significant contribution of loop quantum gravity is its potential explanation for the Big Bang. According to this theory, the Big Bang was not the beginning of time, but rather a transition from a previous contracting phase to our current expanding phase. This idea, known as the Big Bounce, implies a cyclic model of the universe, where each cycle begins with a bounce rather than a singularity. This perspective provides a new way of thinking about the origins and evolution of the universe. Loop quantum gravity and string theory represent two different but complementary approaches to understanding the fundamental nature of the universe. While string theory attempts to unify all fundamental forces through the vibrations of strings and higher dimensional branes, loop quantum gravity focuses on the quantization of spacetime itself. Both theories offer profound insights and face significant challenges, and it is possible that the true theory of everything will incorporate elements of both approaches. The search for a unified theory is not just a quest for a set of equations that describe all physical phenomena. It is also a journey to understand the deepest principles that govern the universe. It challenges us to rethink our assumptions about space-time and matter and to explore the fundamental nature of reality. The pursuit of a theory of everything reflects our innate desire to find order and coherence in the cosmos, to uncover the underlying unity that connects all things. As we continue to explore these theories, we are reminded of the power of human curiosity and the drive to understand the universe. The search for a unified theory pushes the boundaries of our knowledge and challenges us to think beyond the limits of our current understanding, inviting us to explore the mysteries of the cosmos with an open mind and a sense of wonder. The journey toward a theory of everything is ongoing, and each step brings new insights and challenges, whether through the elegant mathematics of string theory, the discrete structures of loop quantum gravity, or some other yet-to-be-discovered framework. The pursuit of a unified theory represents the pinnacle of human intellectual achievement, a testament to our enduring quest to understand the universe and our place within it. Through the study of string theory, loop quantum gravity, and other approaches, we gain a deeper appreciation for the interconnectedness of all things, reminded that the quest for knowledge is an ongoing journey, one that requires creativity, perseverance, and a willingness to embrace the unknown. When we look at the universe on a grand scale, we see a remarkable tapestry of cosmic structures. Galaxies, clusters, and superclusters form a complex web revealing the vastness and interconnectedness of the cosmos. Galaxies are the fundamental building blocks, each containing billions of stars, planets, and other celestial objects bound together by gravity. Our own Milky Way is one of these immense star systems, spiraling gracefully through space. Galaxies do not exist in isolation. They are grouped into clusters, which can contain hundreds or even thousands of galaxies. These clusters are gravitationally bound, meaning that the galaxies within them orbit a common center of mass. The interaction between galaxies within clusters often leads to spectacular phenomena such as galaxy collisions and the formation of new stars. Even larger than clusters are superclusters, which are vast assemblies of galaxy clusters. These enormous structures are among the largest known in the universe, stretching across hundreds of millions of light years. Superclusters form a cosmic web, with filaments of galaxies and clusters connected by vast voids of empty space. This web-like structure is the result of billions of years of gravitational interactions and the expansion of the universe. One of the most intriguing aspects of the large-scale structure of the universe is that much of it is invisible to us. This brings us to the concepts of dark matter and dark energy, which together make up most of the universe. Despite their names, these components are not directly observable because they do not emit, absorb, or reflect light. However, their presence is inferred from their gravitational effect on visible matter, radiation, and the large-scale structure of the universe. Dark matter is believed to make up about 27% of the universe's total mass and energy content. It does not interact with electromagnetic forces, which means it doesn't emit light or energy that we can detect with current instruments. However, we can observe its gravitational effects on galaxies and clusters of galaxies. For example, galaxies rotate faster than can be accounted for by the visible matter alone. The additional gravitational pull needed to explain this rotation is attributed to dark matter. Without it, galaxies would not hold together as they do. Dark matter is thought to form a scaffolding for the universe, clumping together under gravity and creating the seeds for galaxy formation. As ordinary matter falls into these dark matter clumps, galaxies are born. This invisible framework helps explain the distribution and movement of galaxies and clusters we observe today. Dark energy is even more mysterious. It is thought to make up about 68% of the universe and is responsible for its accelerated expansion. This expansion was first observed in the late 20th century when astronomers discovered that distant galaxies were moving away from us faster than expected. Dark energy acts as a repulsive force, counteracting the pull of gravity and causing the universe to expand at an increasing rate. Despite its profound effects on the cosmos, the nature of dark energy remains one of the biggest mysteries in cosmology. The Lambda CDM model is the standard model of Big Bang cosmology. Lambda refers to the cosmological constant, which represents dark energy in Einstein's field equations of general relativity. CDM stands for cold dark matter, which refers to dark matter particles that move slowly compared to the speed of light. This model provides a comprehensive framework for understanding the evolution and structure of the universe from its earliest moments to the present day. According to the Lambda CDM model, the universe began with the Big Bang, a rapid expansion from an extremely hot and dense state about 13.8 billion years ago. As the universe expanded, it cooled, allowing particles to form atoms and eventually leading to the formation of stars and galaxies. The model explains the observed large-scale structure of the universe, the cosmic microwave background radiation, and the abundance of light elements such as hydrogen and helium. The Lambda CDM model also accounts for the accelerated expansion of the universe due to dark energy and provides a framework for understanding how dark matter influences the formation and evolution of cosmic structures. Despite its successes, the model is not without its challenges. For example, the exact nature of dark matter and dark energy remains unknown, and there are discrepancies between the model's predictions and certain observations, such as the rate of cosmic expansion. Studying the large-scale structure of the universe and the role of dark matter and dark energy requires sophisticated tools and techniques. Observations from ground-based telescopes, space-based observatories, and cosmic microwave background experiments all contribute to our understanding. These observations allow scientists to map the distribution of galaxies, measure the effects of dark matter and dark energy, and test the predictions of the Lambda CDM model. One of the key tools in this research is the cosmic microwave background, CMB, radiation. The CMB is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of the universe when it was just 380,000 years old. Studying the CMB allows cosmologists to glean information about the universe's early conditions and the nature of its constituents. Gravitational lensing is another important technique, allowing scientists to map the distribution of dark matter. When light from distant galaxies passes near massive objects, such as galaxy clusters, it bends and distorts the light due to gravity, a phenomenon known as gravitational lensing. By studying these distortions, astronomers can infer the presence and distribution of dark matter, providing valuable insights into its role in cosmic structure formation. As technology continues to advance, upcoming missions like the James Webb Space Telescope will further enhance our understanding of the universe. This telescope is designed to observe infrared light and will allow astronomers to study distant galaxies, the formation of stars, and the evolution of cosmic structures in unprecedented detail. The quest for knowledge about the cosmos raises profound questions about the nature of reality and our place within it. The participatory anthropic principle posits that observers play a crucial role in the universe's properties and existence. According to this principle, the universe is fine-tuned for the existence of observers, and its fundamental parameters must fall within certain ranges to allow for the emergence of conscious beings. This raises philosophical questions about the relationship between consciousness and reality, suggesting that observation is not merely a passive act, but a dynamic process that influences the universe. Quantum mechanics adds another layer to this discussion, particularly with the concept of wave function collapse. In quantum mechanics, particles exist in a superposition of states until they are observed, at which point they collapse into a definite state. This raises questions about the nature of reality and the role of the observer in shaping it. The idea that consciousness may play a role in determining the properties of the universe challenges our traditional notions of an objective reality, suggesting that the universe may be more interconnected and interdependent than we previously thought. In conclusion, the exploration of string theory, loop quantum gravity, cosmic structures, dark matter, and the philosophical implications of observation invites deeper reflection on the fundamental nature of the universe. The quest for a unified theory is not just a scientific endeavor. It is a journey toward understanding the interconnectedness of all things and our place in the cosmos. Each new discovery sheds light on the mysteries of the universe and encourages us to embrace the unknown with curiosity and wonder, which is believed to have a subsurface ocean beneath its icy crust. The mission will investigate the moon's potential habitability and search for signs of life. Dragonfly, set to launch in 2027, will send a rotorcraft to Saturn's moon Titan, exploring its diverse and complex environment. Titan's thick atmosphere and surface lakes of liquid methane and ethane make it a fascinating target for studying prebiotic chemistry and the potential for life. The advancements in cosmology and space exploration are not just about collecting data and making discoveries. They also involve the development of new technologies and techniques that can have broader applications. For example, the technology used in adaptive optics for telescopes is also being applied in medical imaging, improving the clarity and precision of images used in diagnostics and treatment. The engineering and problem-solving required for space missions drive innovation in materials science, robotics, and other fields, leading to benefits beyond astronomy. Hypothetical scenarios and speculations. The exploration of hypothetical scenarios and speculations in cosmology opens up some of the most intriguing and mind-bending questions about our place in the universe. These ideas push the boundaries of our understanding and challenge us to think beyond the known and the observable. Among these fascinating topics are the Fermi paradox, the simulation hypothesis, and the possibility of alternate dimensions. The Fermi paradox is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This paradox highlights the contradiction between the high probability of extraterrestrial life in the universe and the lack of evidence for or contact with such civilizations. Given the vast number of stars and planets in the Milky Way galaxy alone, it seems statistically likely that intelligent life should have arisen elsewhere. Yet, despite our efforts to detect signs of extraterrestrial life through programs like SETI, Search for Extraterrestrial Intelligence, we have found no definitive evidence. Several explanations have been proposed to resolve the Fermi paradox. One possibility is that intelligent civilizations are rare or short-lived. Life might frequently arise, but the development of advanced technological societies could be an infrequent event. Alternatively, civilizations might self-destruct before they can establish contact with others, through wars, environmental degradation, or other self-inflicted disasters. Another hypothesis suggests that advanced civilizations may choose to avoid contact with us. They could be observing us silently, either to allow us to develop independently or because they have ethical reasons for non-interference. This idea is sometimes referred to as the zoo hypothesis, where Earth is seen as a kind of cosmic zoo being observed by advanced extraterrestrial beings. It is also possible that we are not looking in the right way or at the right times. Advanced civilizations might use communication methods that we do not yet understand or are unable to detect with our current technology. They might also be located in regions of the galaxy that are difficult for us to observe. These possibilities highlight the limitations of our current search methods and the need for innovative approaches to finding extraterrestrial life. The simulation hypothesis presents another profound and speculative idea about our reality. Proposed by philosopher Nick Bostrom, this theory suggests that our universe might be an artificial simulation created by a highly advanced civilization. According to this hypothesis, it is possible that future civilizations, with computational power far beyond our own, could simulate entire universes, including conscious beings within them. If such simulations are possible and numerous, then it is statistically plausible that we might be living in one. The simulation hypothesis raises profound questions about the nature of reality and our place within it. If we are living in a simulation, then what we perceive as physical reality might be nothing more than a complex digital construct. This idea challenges our understanding of existence and the fundamental nature of the universe. It also leads to philosophical questions about the purpose and meaning of life within a simulated reality. One potential way to investigate the simulation hypothesis is to look for anomalies or inconsistencies in the laws of physics that might suggest an artificial origin. Some scientists have speculated that certain unexplained phenomena, such as the behavior of subatomic particles or the nature of dark matter, could be clues to the underlying structure of a simulated universe. However, proving or disproving the simulation hypothesis remains a significant challenge, as it requires a level of understanding and technology that is currently beyond our reach. The concept of alternate dimensions is another speculative area of cosmology that captures the imagination. The idea that there could be higher dimensions beyond the familiar three dimensions of space and one of time is a cornerstone of theories like string theory. In string theory, additional dimensions are compactified or curled up in such a way that they are not observable at everyday scales. These higher dimensions could have profound implications for our understanding of the universe. If higher dimensions exist, they could influence the behavior of fundamental forces and particles in ways that we do not yet fully understand. For example, gravity could be stronger or weaker in different dimensions, which might explain some of the anomalies we observe in the behavior of galaxies and cosmic structures. The existence of higher dimensions could also provide a framework for unifying the fundamental forces of nature, offering a more complete and coherent picture of the cosmos. The possibility of alternate dimensions also opens up fascinating speculative scenarios. Some theories suggest that there could be parallel universes or branes existing in higher dimensional space, each with its own unique properties and physical laws. These parallel universes might occasionally interact with our own, leading to observable effects such as unexplained cosmic events or anomalies in the behavior of particles. The exploration of alternate dimensions is not just a theoretical exercise, but also has practical implications for our understanding of the universe. Experiments at particle accelerators like the Large Hadron Collider, LHC, are probing the fundamental nature of matter and energy, searching for evidence of higher dimensions and other exotic phenomena. These experiments push the boundaries of our knowledge and could potentially reveal new insights into the fabric of reality. As we contemplate these hypothetical scenarios and speculations, we are reminded of the vastness and complexity of the universe. The Fermi paradox challenges us to consider the possibility of extraterrestrial life and the factors that might influence its detectability. The simulation hypothesis invites us to question the nature of reality and our place within it. The exploration of alternate dimensions expands our understanding of space and time, opening up new possibilities for understanding the cosmos. These speculative ideas highlight the importance of imagination and creativity in scientific inquiry. They push us to think beyond the boundaries of current knowledge and to explore new frontiers in our quest to understand the universe. While these ideas may seem far-fetched or speculative, they also represent the cutting edge of scientific thought, challenging us to expand our horizons and consider the deeper mysteries of existence. Each new discovery and each new theory brings us closer to understanding the profound questions that lie at the heart of cosmology. The exploration of these ideas not only expands our knowledge, but also inspires us to think deeply about the nature of reality and the fundamental principles that govern the cosmos. As we contemplate the universe's mysteries, its vastness, its origins, and its hidden dimensions, we find ourselves on the edge of human understanding, reaching toward realms of thought and science that are both humbling and inspiring. Questions like whether life exists beyond Earth, if we're part of a grand cosmic simulation, or if alternate dimensions ripple through our universe, spark a sense of wonder that's as old as humanity itself. The journey to uncover these answers is a testament to our innate desire to understand not just our world, but our very place in the cosmos. The Fermi paradox challenges us to reflect on our solitude in the vastness of space, urging us to think about how we might someday make contact with other civilizations. The simulation hypothesis dares us to question the very fabric of our reality, leading us to wonder if our universe is but a shadow cast by a more advanced intelligence. And the idea of alternate dimensions suggests an uncharted complexity of existence, where other worlds might coexist with ours, waiting to be unveiled. As we advance our technologies and refine our theories, we inch closer to these mysteries, but every answer reveals new questions. The observable universe may be all we can see, but what lies beyond continues to inspire a sense of limitless possibility and boundless curiosity. These questions remind us that, as much as we uncover, we're part of an ongoing story, an endless cosmic tapestry woven with light, time, and possibility. In our quest for knowledge, we are reaching not just across space, but into the very essence of existence. This journey brings us together, inspiring awe and wonder across cultures and generations, uniting us in our shared curiosity about the cosmos. As we continue to explore, we may one day uncover answers to questions we can scarcely imagine today. Thank you for joining us on this incredible journey through the mysteries of the universe. If this exploration inspired you, don't forget to like, subscribe, and share. Together, let's continue to reach for the stars, for as long as questions remain, there is always more to discover. Until next time, keep looking up, keep wondering, and keep reaching beyond the horizon.